Hello, everyone. Can I ask you guys to stop talking, please? Thank you. So today, we're going to start talking about but before we kind of really get into what Chapter 4 is all going to be about, I have some vocab and some definitions that I want to run through before we kind of narrow it down into what Chapter 4 we're actually going to be doing. So Chapter 4 and Chapter 5 are quite related. Chapter 4 is like a special case of what we're doing in Chapter 5, and then Chapter 5 is the more general situation. So we're just going to spend a little bit of time here to start, just running through some basic vocabulary. Okay. So starting with some definitions. So we're first going to start by defining something called a polynomial. A polynomial is just the sum or difference of monomials, which is probably not a terribly helpful definition because what is a monomial, right? So that's the next thing that we'll define then. Yes. Okay, so a monomial is the product of a variable with a non-negative whole number exponent and a real number. So a polynomial is just a bunch of these monomials being added or subtracted, or added and subtracted. So let's just do a couple of examples here, or actually probably more like several, just to make sure that we can figure out what's a monomial. Thank you. That seems excessive, but okay. Oddly specific, it's just a sneeze.
You know what your soul was?
Well, it seems like a lot for...
It's the soul. I'm sorry, God bless your soul. I see your notes.
And body.
No, it's the soul.
And beard.
All right. So, we're just going to do some examples here. We're going to decide whether these objects, or these that I write down, meet the criteria of being a monomial or not. Okay? How about 3x squared?
Yeah.
So is this the product of a number and a variable?
Yes.
Does the variable have an exponent that's a non-negative whole number?
Yes.
So what do we conclude then? This is a monomial. What about this? Be careful.
Oh, yes, because it's...
What's the real number? 1. Yeah. Remember that there is like a 1 there that we know exists, but we don't write down. Okay.
Is there one exponent or no?
What do you think?
Yeah.
Yeah, there is. So again, remember that there's a 1 exponent that we never write in. So that meets the criteria. So far, so good? Well, this is maybe an unfair question because probably we don't know this. The answer here is yes, because the way we justify this is 10 is equal to 10 times 1, right? And 1 is the same thing as x. And if I look at this, that does meet the criteria for a monomial. The thing that's unfair is that you don't know that anything to the 0 power is equal to 1 other than 0. So the takeaway, though, is just like a plain old number does meet the qualification of being a monomial. So there's two things that we're getting confused on. So the number that we're multiplying by doesn't need to be a negative, doesn't need to be positive, it doesn't need to be a whole number. Right? But if we flip this, that's no. Or not a whole number in the exponent. So it fails on 2 regards in the exponent. Is that okay? What if we have this? No. What if we did this? Good. What's wrong with that one? Okay. What about this? No. Right? 0.3 isn't. What about what are we unsure about?
X is over 5 the only variable.
Correct. What's the definition say? For a monomial, yeah. What does it have to be? Okay. So if we go back and we look at it, it's the product of a variable and with a non-negative whole number exponent and a real number.
No. A factor. It's not a product.
So you're saying it's not a product. Put it this way. Isn't that the same thing? So this should be yes. Right? 2 times 1/3 is 2/3, right? What if we did it this way, though? That's no. So the takeaway is if the x isn't the variable's in the exponent, or I'm sorry, the variable's in the numerator, monomial. Variable in the denominator, not monomial. What if we do this? Is this a monomial? This is no.
Oh, sorry.
Why is it not? Well, what's going on between the real number and the variable? Is it multiplication? No, the variable's in the exponent, right? That's different than multiplication. Not a monomial. Is everybody good with that? Okay. Do we feel like we have a pretty good picture of what's a monomial and what's not? I feel like I went through all the little tricky things that could come up. All right. So the next thing we're going to do is we're going to talk about some polynomial vocabulary. So let's say we have a monomial. That monomial is negative 3x to the fifth. We call this negative 3 out front the coefficient. And we call the exponent the degree. Is everybody okay with that? Okay. Now, if we look at a monomial, it's just the sum or difference of a bunch of monomials, right? No. So is this polynomial? Right? Agreed, right? Each one of these things is a monomial that are being added or subtracted. Everybody agree? Okay. So the first thing is we want to talk about how many monomials do we have here? 4, right? Each one of these monomials we call a term. And then we have our coefficients. What just happened there? All right, so we have negative 10, 3, and negative 5. Is that okay? The degree of the polynomial is the biggest exponent. And the coefficient for the monomial term with the biggest exponent gets a special name. We call this the leading coefficient. Correct. Well, then you'd add them together. So there would only be one of them. You know, if you had 7x squared plus 10x squared, you just call that 17x squared, right? So if you have 2 of them with the same degree, then you can add them together. So you still just have one of them, you know what I mean? Okay. And then there's one more special term. It is this guy. This is the constant term. The term with no variable is the constant term. So the leading is the coefficient on the term with the biggest degree.
Oh, okay.
So it's not the biggest coefficient, it's the coefficient on the term with the biggest degree.
Okay.
Jack?
Is there always going to be a constant term?
Is there always going to be a constant term? Yes. We'll see why in a second. Sound good? So I'm just going to give you the polynomial and then ask you to identify some of these parts for it, okay? What? You made some noise.
I was just stretching and yawning at the same time.
Oh, that's awkward. Okay, so let's say we have this polynomial here, 12x plus 6x squared minus 10 plus 5x cubed minus 7x to the fifth. And I'm going to ask how the number of terms, the degree, the leading coefficient, the constant term, so LC, leading coefficient, CT, constant term. Is everybody okay there? So how many terms do we have here? 5, good. Because we have 1, 2 polynomials. Everybody agree with that? What's the degree?
5.
5, why?
Because that's the highest exponent.
Excellent. That's the biggest exponent. What's our leading coefficient here?
12.
So 7, 12, or negative 7, I've heard.
Oh, negative 7.
Negative 7.
That's the negative.
Everybody's okay with it? It's the coefficient on the biggest degree term. Not the first coefficient, not the biggest coefficient, but the coefficient on the biggest degree term. And then the constant term is negative 10. Okay. What if we ask the same thing about this? Why is it not a polynomial? Well, what's the definition of a polynomial? It's the sum or difference of monomials. Is this the sum or difference of monomials? Okay. How many terms do we have? 2. What's the degree? 5. What's the leading coefficient? 3. What's the constant term? So I've heard doesn't have one, which is technically incorrect. 0 is correct. Why is the constant term 0? Isn't this still the same thing if I write a plus 0 at the end? I haven't changed anything, right? Is 0 a monomial? Yeah, because we said just a regular number is a monomial. So is there always a constant term? Yes. It just might be 0 if you don't see it written down, but it's always there. Does that make sense? I didn't mean to trick you there, Jack, but it was a good question that you asked about, and I wanted to I answered it that yes, there is always one. It was not how you expected that to work, I think, but that's okay. Does everybody feel okay with this vocabulary, though? Should be relatively straightforward. Okay. As soon as my computer wants to stop being a laggy so-and-so. Oops. So the next thing I want to do is talk about ways to classify polynomials. Except I started spelling polynomial wrong, and this is literally how slow my computer is lagging. So the first way that we have to describe or to classify a polynomial is classifying it by degree. The degree is 0. We call this a constant polynomial. So something like 10 would be a constant polynomial. If the degree is 1, some things are both examples of linear polynomials. Degree is 2. We call this a quadratic polynomial. So for example, 2x squared, or we could have 2x squared plus 5x minus 3 or something. To do 3, we call this a the third, or 7x the third minus 2x plus 5. Oh my God. So if we have a degree 4, we call this a quartic polynomial. And that's as far as I would worry about you guys knowing the special names for. Anything with a bigger degree than this, we'll just kind of name by its degree. God. You're impossible, computer. So anything that's bigger than degree 4, we'll just call it that degree. So we'd say like, oh, this is a degree 5 polynomial, or this is a degree 10 polynomial. The other way that we'll classify polynomials is by the number of terms. Two terms we'll call a binomial. 3 and then anything bigger, just classify with the number. So if something had 4 terms, we'll just call it a 4-term polynomial. Is that okay? Pulls up, yes, of course. Let's just do some examples where we classify some of these by their degree and number of terms here. So let's say we have 3x to the third plus 10x. What's the... This is degree 3. And the number of terms is 2. Since it's degree 3, we'd say it's cubic. And since there's 2 terms, we'd say it's a binomial. So this is a cubic binomial. What is going on? There's so much. Okay. What if we have the polynomial negative 10x to the fourth minus 7x squared plus 6? What's the degree for this one? 4. And the number of terms is 3. Tick, because it has 4, or degree 4. Trinomial, because there are 3 terms. Right, we've just made some names up and talked about some vocabulary and like what we call different parts of things, but we haven't done any real mathematics yet, right? There's been no computation, there's no calculations involved, there's no graphing or anything else. It's just kind of talking about how well we're going to about some things, language that we can use to communicate. So we've been talking about polynomials in general here, and we will do that in great detail in Chapter 5. But in Chapter 4, we're going to be spending that whole chapter talking specifically about quadratic polynomials. And this is a pretty common practice in mathematics, or before we talk about the most general situation, we begin by talking about like a simpler special case. Yes?
What was the one term called for the number of terms?
Monomial, which we knew already. No problem. I don't mind repeating if you missed something. It's okay. Okay, so quadratic polynomials. That's what we're going to be talking about. We're going to spend one of these chapters focusing on skills. Simplifying, solving, and graphing. And we're going to do that here in Chapter 4, talking about quadratic polynomials. And I don't know that we'll go necessarily in this specific order when we talk about these things, but these are the 4 major skills that we're going to be worried about kind of acquiring in this chapter. I do know that today we're specifically So we're going to start our discussion of simplifying quadratic polynomials by first identifying 3 forms in which we commonly write our quadratic polynomials. And then we're going to spend the rest of today kind of talking about how we move back and forth between these different forms. Okay with that plan? Okay. The first way is called standard form. And what standard form looks like is ax squared plus bx plus c, where a, b, and c are the coefficients. So for example, let's say we have the polynomial negative 2x squared plus 5x plus 10. Is this in standard form? Yes, right? You can tell because it goes from quadratic term to linear term to constant term in the same order as the form that we described before. What would be the value of the A coefficient? Well, A would be -2. What's the value for the B coefficient? And the value for the C coefficient would be? Is everybody good with that? So far, so good? Okay. So 10 minus 3x squared minus 7x. Is this written in standard form? No. What's wrong with it? The terms are in the wrong order, exactly right. So how would I need to write this so that it was in standard form? What's going to come first? Negative 3x squared, and then minus 7 plus 10. Everybody good with that? Okay. So what would the values for A, B situation? What's A? Just -3. Remember, the A, B, and C are coefficients, not the whole term. So they're just the number part in the front. The value for B is -7, and the value for C is 10. So the important takeaway here is that regardless of the A is the part attached to the quadratic term, the B is the part attached to the linear part, or C is the constant term, right? So the order which we write them doesn't change the values of A, B, and C. Those are fixed based on what term they're the coefficient of. Let's do one more tricky one. Is this in standard form? Sure. What's the value for A, B, and C? Okay, A is 1. Good. Right, because you could really think about this as x squared, like 1x squared plus 0x plus 0, right? Everybody's happy with this? Feel comfortable about what a standard form quadratic looks like? Okay, good. Called factored form or intercept form. So your intercept form or factored form is A times the quantity x minus p times the quantity x minus q, where those A, P, and Q are just constants. They're just like regular old numbers. So let's look at a couple of examples here. This first example, 4 times the quantity x minus 5 times the quantity x plus 1. Is this in factored form?
Yeah.
Okay, yes, good. Since it is, what are the values for A, P, and Q? A is 4. Be careful. P is 5. Why is P 5? Notice there's a negative sign already in the form. Plugged a positive 5 in for P, I'd have x minus 5, right? Which is what we have below. Does everybody see that? What's this remind us of a little bit? Absolute value functions, the H is always kind of the opposite sign of what it is. What's our value for Q then? -1. Is everybody good with that? Same reasoning, right? Okay. Is this in factored form? What's wrong with it, the people that have said no? Ella, do you have an idea there? You're not Ella. Riley. Well, you shook your head. Well, it's not. It's not in factored form. There's something wrong with this. Okay, the number's not in the front. So there's no A. But couldn't the A just be 1? Bianca? There's X's, right? Yeah, this is the issue, is our X's must be 1 in the factored form. But here in example B, we have one of the X's has a coefficient of 2. Can we see that? Can we fix this, though, so it is in factored form? Yes, is the answer to this. That first set of parentheses, is there something in common between 2 and -6? 3 is in common between 2x and -6? 2, right? Everybody agree with that? That each of those two terms are divisible by 2. So we'll factor a 2 off. When I factor that 2 off, what am I resulting with? Or what results? Or what do I have left? Very good. So remember this process that we just did was called factoring a greatest common factor. When we do that, we're dividing it back off. So I did 2x divided by 2 gave me the x. And -6 divided by 2 gives me the -3. And whatever we divided by goes out front, right? The check for you to make sure that you know that you've done it right is that if I distributed that 2 back through, I'd be left with the original. Everybody see that? That's just me pointing out that if you wanted to check, you could do that. What's our values for A, P, and Q then? 2 for A. So far, so good? Pretty comfortable? Okay. The last here is called Vertex Form. Oops. Is A times the quantity, x minus h squared plus k, where A, h, and k are just constants. So -3 times the quantity, x plus 4 quantity squared plus 2. Is this in vertex form?
Yeah.
Okay, I agree. What are the values for A? -4, very good, and 2. Is everybody okay with that? Notice the h is that same tricky thing where we had a negative sign in the formula, so the h is always the opposite of whatever it appears. Sound good? Good. I don't know what just flashed up at me. What happened here? Is everything still working? I think it is. Okay. I don't know. Something just flashed on my screen for a second. Did you guys see it? Could you tell what it was? Okay. I couldn't either. But all right. So and what we're going to be focusing next day or so is how to change back and forth between these 3 forms. So this is our little roadmap for how to do that. So I have Intercept Form, which I abbreviated IF, Standard Form, which I abbreviated SF, and Vertex Form, which I've abbreviated VF. And then I have some arrows pointing in each direction. So for example, to move from Intercept Form to Standard Form, we're going to use FOIL. To go from Vertex Form to Standard Form, we're going to expand and then distribute. To go from Standard Form to Intercept Form, we're going to factor. And then to go from Standard Form to Vertex Form, we're going to do a process called completing the square. And I abbreviate that as CTS because, well, that's too many letters for me to write all the time. Completing the square? That's what I wrote above it. So far, so good? Okay. So let's look at some examples of how we do each of these 4 steps. Okay? We're not going to get to all 4 of them today, but that's okay. Okay. So this first transformation or change in form, we're going to be going from an intercept form to standard form. And we said the process to do this is called FOIL. If you remember, FOIL is an acronym. It stands for first, outer, inner, last. And it's just describing how we multiply 2 sets of parentheses together like this, or 2 binomials together. So first means we're going to be multiplying the first things in the parentheses together. So x times x gives us x squared. The outer means we're going to be multiplying the outside parts of the parentheses together. So x times -7 is -7x. Inner means we're going to multiply the inside parts of our parentheses together. 3 times x gives me 3x. And then last says we're going to multiply the last things in each parenthesis together. So 3 times -7 is -21. And then the last thing we need to do here is just combine any like terms. Hopefully you notice that -7x and +3x could be added together. And we do that just by adding the coefficients. So -7 plus 3 is -4. So that's a -4x. And that's a standard form polynomial, so we'd be done. Is everybody okay with that? Hopefully that feels pretty familiar. FOIL is something that you should have done in your Algebra 1 class, or maybe even your pre-algebra class. And hopefully we feel pretty comfortable with that skill. Let's look at one example here, because there's one other thing that could come up that sometimes throws students for a loop. So let's do that in advance. So this is still in intercept form, right? Even though we have this coefficient out front. And this coefficient can sometimes trip up students. So how do I deal with that? Well, so if you remember, way back in like your pre-algebra classes, you would have talked about if we multiply 3 things together, we can either multiply the first 2 things and then multiply the third thing, or we could multiply the last 2 things and then multiply the first thing, right? That's what we're going to do here. So that means that I could either distribute the 2 inside the x minus 7 and then take the result and multiply it by the x minus 5, or I can multiply the x minus 7 and the x minus 5 and then take the result and multiply the -2 through. Either of these is okay to do. What's not okay to do, and I see happen quite frequently with students, is them to do something like this, where they multiply the -2 to both sets of parentheses, and then multiply multiply those 2 sets of parentheses together again. This is bad. Do not do this. The -2 only gets multiplied in 1 set of parentheses, not both. Okay? This would be equivalent to saying, oh, if I had 2 times 3 times 5 to go, okay, I'll do 2 times 3, and then I'll do 2 times 5 and multiply those together. That's like what you're doing there, which is nonsense, right? Nobody would do that. If I asked you to do 2 times 3 times 5, you do 2 times 3 is 6, 6 times 5 is 30, and you're done, right? Nobody would do that crazy stuff going on. But as soon as we put in some variables and some extra parentheses, you know, like all of our common math sense kind of goes out the window sometimes, and that's okay. That's why I'm showing you, you know, some of these common mistakes is so that we can avoid them and not make them. So up here, it doesn't matter which one of these 2 that we do. They're equivalent to doing the same thing. Personally, I like doing this because I think the foiling is easier if the numbers are smaller. Distributing the 2 in is just going to make the numbers bigger and make the foiling a little bit more tedious, so I like to do it last. But it doesn't matter. You can try one or the other, just pick one and do it all the time, or see which one works better for you or whatever. They're both doing the same thing, so I just know the one that I like, and I'm going to tell you that I'm doing that one with bias because that's just the way I like to do it. You know what I mean? Okay. So, if I FOIL this out, first, outer, inner, last. And then I'll combine my like terms. -5 minus 7 is -12. And I just distribute that -2 through. And there we go. Everybody okay with that? Again, I made kind of like a long-winded explanation for something that was relatively simple. But I want to explain why we're going to do it the way we're doing it and not do it another way. I think that's important because when it comes to a more pressure-filled situation, like you're taking a test or something, it's easy for common sense to go out the window. And if you have a good explanation as to why, it makes it harder to decide to make something up. Makes it easier to remember if it makes sense as to why we're doing it this way. Hopefully, anyways, right? We feel okay about this foiling idea? The next thing we want to look at is going from vertex form to standard form. So we said we did that by expand and distribute. So let's say we have -4 times the quantity, x plus 3, quantity squared, plus 10. So the distribute shouldn't be an issue, right? We know what distribute means. Expand is the word in there that maybe we don't really know what that means, right? So let's say we have something like x squared. We know x squared is the same thing as, actually, let's not say x squared. Let's say a squared. A squared is the same thing as a times a. Everybody agree with that? So if we go back to our problem here, we're going to use this notion of expanding to deal with x plus 3 squared. So if I use that notion of expand, x plus 3 squared must just be x plus 3 times x plus 3. Everybody okay with that? And now this looks remarkably like the previous problem. Everybody agree with that? So I'm going to go ahead and do my foiling. And then I'll combine my like terms inside that parenthesis. So 3x and 3x is 6x. And then we'll distribute the -4. And then I'll combine the -36 and the +10. And there's my standard form polynomial. Are we okay with that idea? So it's almost identical to the previous kind of problem, right? We just have to know what do we mean by expand, and make sure that we do this first step where we separate that out. What are the common mistakes here? First common mistake I see students make is they do this. What did we do here? What did the student do that was wrong? Yeah, they distributed the exponent. You can never, ever, 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 ever distribute an exponent. Okay, it's not a distributive operation. Do not do that. Okay, the way you deal with the exponent is you expand. Okay, also bad. So here's the problem. The other thing that I'll see students do is this. What did they do there? Yeah, they distributed the -4 into the parenthesis. Why is that wrong? Remember what the order of operations is. Exponent should come before multiplication, right? Did we deal with the exponent before you distributed? You did not. That is the problem there. Is everybody okay with that idea? Again, I'm showing you these things because every year I see students do these and get like hooked on doing these processes that are incorrect because probably they weren't pointed out that they are wrong beforehand, and they're easy things to assume you can do because they look like stuff that we do, right? That's why I want to take some time here in the beginning and point out what not to do before you start doing it and create a bad habit. So that's the point of me going through and painstakingly like pointing out these things that you're like, who would do this? Every year, many students do these. Like that doesn't make it dumb, right? Like this is common stuff that happens, but I'm trying to make it less common by pointing it out beforehand. And if you still make these mistakes, don't feel bad, but try to be mindful about when you're doing the process that you're not, you're remembering what the process is and not just trying to like figure it out yourself. Or at least if you are trying to figure it out yourself, you're not doing something that's on the bad list, the naughty list. Okay. The next one that we're going to talk about is going from standard form to intercept form. And the process there we said is factoring. Yes. Sure. Now, of all the things we do in first semester, this skill is the most important thing that we do in first semester. You're going to need it a bunch in the following chapters, a bunch in second semester, a bunch in the years following this. In mathematics, this is going to be something that people are going to assume that you can do quickly and in your head for some of these easy situations immediately following this class. And even in later, future in this same class, we're going to assume that you can do this skill quickly, effectively, in your head. No, I'm good. We're teaching. So it is quite important. Okay? We're obviously not going to finish talking about this skill today if it's this important. We're going to go into next week or into next class talking about this for sure. We're going to spend time in next class just doing practice on this after we've done some as a group. We'll do some individual practice on this because this is something that if it's this important as I'm saying it is, it's important that we get a lot of practice on it. And you need practice with some guidance where you can ask questions and get stuck on things and check your work and go back and try it again and all that sort of thing. So all I want to do here to start with is just kind of talk about the idea. So factoring is FOIL in reverse. So for example, let's say we have x plus 3 times x minus 5. If I FOIL that out, I'd have x squared minus 5x plus 3x minus 15. And if I combine like terms, that's x squared minus 2x minus 15. Thank you. Yeah, that too. Everybody okay with that? So this side, what we're going to do is FOIL. The other side, what we're going to be doing is factoring. So the first step is going to be to somehow get that standard form polynomial to look like this intermediate step in our factoring step. So to do that, what we need to do is figure out how to break up negative 2x and know that we're supposed to write that as negative 5x plus 3x. Right? Notice that those are still equivalent expressions. 2x is the same thing as negative 5x plus 3x. But how in the world do I know to break it up into 5 and 3, or negative 5 and positive 3, if I haven't already done that? This is the trickiest step. So to do this, we need to answer the question, what two numbers multiply to get A times C and add to get B. And when I say A, B, and C here, I'm talking about the coefficients A, B, and C for my standard form polynomial. So what two numbers multiply to get A times C and add to get B? So for our polynomial, what are our values for A, B, and C here? Well, A is 1, B is negative 2, and C is negative 15. So what I need is I want the two numbers, I'm going to call those numbers M and N, that multiply to give me 1 times negative 15 and add to give me negative 2. Okay, so what we're going to do to find those two numbers that satisfy that is we're going to do this by inspection. So we're just going to answer one of the two questions and then see if that answer also works for the other one. The question that we're going to start with answering is always the multiplication question, because there's only finitely many whole numbers that multiply to give us negative 15. There's infinitely many pairs of whole numbers that add to give us negative 2. So things that multiply to give me negative 15. Well, how about 1 and negative 15? Do those add to give me negative 2? No. How about negative 1 and positive 15? Do those add to give me negative 2? No. What's another pair of numbers that multiply to give us 15? 3 and 5. One of them has to be negative, though, because we need a negative 15. So negative 3 and positive 5. Do those add to give me negative 2? No, they're giving me positive 2. But if I switch the signs, 3 and negative 5, that works. So what I do then is I use those two numbers to rewrite this as that. We'll stop here because I think we're out of time. We'll pick up where we left off on this next time. I don't have anything for you guys to work on for next time. You guys can just relax and try to soak in everything that we did today because there was a lot of information. Not a lot of calculation, but there's a lot of vocabulary and stuff to kind of get comfortable with. Okay?
So are you